Thank you very much, Makoto, for the introduction, and thank you for the organizer for the invitation, and to the local organizer for everything they've been doing this week. It's been a very pleasant stay. It's really nice to see so many familiar faces after so long. It's been really enjoyable. So I'm going to talk today about like a very solo project that I started 2 years ago, so I'm very excited to finally talk about that on a blackboard. That's my second talk about that. This is, the title is Forest-skein groups. So originally this is forest groups, but I had at least 3 people who complained about the title. 2 of them say it was like Forest-skein, so okay, that's fair enough. But some others say more meaningful comments, like saying that you don't really catch what is new in this framework. So Zaremski suggests this other name that I think I'm going to keep here. So what I'm going to do is at first I'm going to introduce what are Forest-skein categories and groups, right? So I start by that because this is really the novelty of the program, is to give you this object, and there are many motivations why I want to do that. So after I give you this object, I'm going to motivate it. It's kind of in reverse. And if I don't do that, I know that I will spend half of the total motivation. So that's why I do that. And the third thing, I'm going to give you the key features of this formalism. All right, why it is so nice. Actually, I'm very happy about this class of mathematical object. And then I will give you results in application. And what I'm going to do is that I'm going to focus on results more in group theory, right? And what you should think that what's really been driven by research here is to have concrete examples, and you can actually compute things, right? So the main application will be, I'm going to give you a beautiful class of groups that have very nice properties and that are rare among groups. Okay. Right. So that's the plan of today. Okay, so what's the definition? And so I'm going to start probably to talk about forest. So I'm going to forest categories. I'm dropping the skin, but you can just put it in your mind. All right, so what is it? Well, the first thing I want to do is to define just a color set. Okay? So I have a non-empty set S of colors. Okay? And from that, I'm just going to create some kind of free category, but where the morphisms are just forest. Okay? So I'm going to look at all kind of diagrams. So S, let's say typically, will be 2 colors, okay, so A and B. Okay, I'm going to look at binary forest, so elements that look like that, where the interior vertex will have various colors. Okay, so I'm going to look at all single vertex. Okay. So I'm going to call F all such diagrams.
So just forests and a function from the vertices to S.
Exactly, yeah. Thank you. Yeah. And here I'm going to stick to binary. Okay. So they are binary rooted finite. Okay. And the roots are here. So these are the roots. Okay. And on top here you have some use. Just some terminology. And what I can do is that I can compose them, and I can, there is a composition, which is just a vertical stacking. Okay? So for example, if I have a forest, which could be a tree, just like that, I compose with something with two roots. So for example, it could be a B here, and here it would be a, let's say. This would be equal to something like that. Okay? Nothing very mysterious. And I take the convention to a bit like concatenation, so I put that on top of it.
And if the numbers don't match?
Then you cannot compose.
Okay.
Yeah. So what you get is, you get a small category. Composition associative, and it's a set. Okay. Here, my set of colors should be non-empty, but it could be infinite of any cardinal, it doesn't matter. So this is kind of
a question.
Yeah.
Identity is formally added then?
Pardon?
Do you draw a line for the identity, or is it just identity?
Yes, some people prefer to have like a point, I draw a line usually.
So the forests can have like lines as well?
Yeah, so for example, I could have do that, and there will be a line. Right? Okay. Okay.
One other question.
Yeah.
Is this about the embedding of the forest numbers itself? So if you had like an A with a B and if you had an A and then a B and an A, is that the same as an A with an A and a B? Like if you flip the output, is it the same graph or not?
Oh, even if I flip that?
Yeah.
No, it's not. It's not, thank you. Yeah. Yeah, so I should say that it's ordered from left to right, you see? The leaves, you cannot change them. So if you have a number isomorphism of graph, you need to be planar, basically, okay? So you cannot do much, it's by isotopy. So if you're used to tensor categories of planar algebra, you can just move around a little bit, yeah. Okay. All right. And now I'm going to put some skin relation. So it's a bit a stretch to call them a skin relation, because in general in planar algebra, you have a linear structure and you have like a linear combination of diagram equal to 0. Here you don't have that, but what I'm going to say is that you are able to remove patterns. So what I'm going to say is that I'm going to decrete that skin relation will be just certain pairs of strings. So let me just give you an example. So I'm going to put FC for forest category. Okay. So here I'm having two colors, A and B. I'm going to put just one relation, so it's not too complicated, and my relation will be the following. Okay, I'm going to say that this is the same as that. Okay. And what does that mean? It means that now you take your categories here, and each time that this tree will appear somewhere inside your forest, it's okay to replace it by this diagram. Right. So the thing that you want to match, to make sense, is the number of leaves here. Here there are three leaves, here 3 leaves. Okay. Okay, so certain pair of trees with same number of leaves.
So this is specific for your two colors now, or?
Yeah, so here I defined one forest category.
Okay.
So it's like a group. You have generators that are the colors for labeling, and then the relations are given by a pair of trees. So this is one example.
One more question. Your leaves, do they end in the middle of the diagram, or do they end on the top boundary?
Yeah, so you can change that anywhere you want inside the diagram. Oh, sorry.
Does this get that end in the middle of the diagram, or does it go up to the top of the diagram?
No, the leaves has to be all the way to the top. So you mean this?
Yeah.
Yeah.
Okay.
So here implicitly I do that. Oh, I'm really sketchy, sorry. I see that it's, yeah. Okay. So here there is 1, 2, 3 leaves, 1, 2, 3, so I'm happy. And so since I only deal with binary forest, it means that I have the same number of carets. You can also see that, like 2 carets. Yeah.
Like, could you also do a relation that identifies one forest with another forest? Like having
yes. So you can do that. You could, instead of taking trees, you could take forest. But in fact, it will not be more general, because imagine you take 2 forests, and then you take all the relations that are this forest and you complete by any trees below. Okay? So you have the same tree below, and in fact, that's the same thing. Right? Okay. So it's also important to have binary to do that, because if not, if you have ternary forest, good luck to go to something with 2 roots, right? How do you do that with a tree? So actually binary make your life much easier. Okay. And if you want, so you could consider the category of all Forest categories like that, and there's a good notion of morphism. I'm not going to define it right now, but it's going to be useful after. Okay, there will be some, it kind of helps the machine to have. Right. So this thing is just one example of a so-called Forest category. And perhaps before I continue, I'm going to give you other examples, right? I'm going to give you, of course, the examples that have motivated this work. That you're going to guess. So let's look at the examples. So first example is, maybe I can write it like that, one color and no relation. Okay. So it's just a classical category of binary forest. And so what I'm going to do, my objective is not to give you a bunch of categories, I want to construct groups. Okay, so I'm going to explain that in a minute, but I cannot resist to tell you what you have here, and you can guess. From this, we can create the so-called Thompson's group. Thompson's group F, okay? And this description is actually not due to Thompson, but the first time it appears in the literature, that's Kenneth Brown who gave it in 1987, so 20 years after the one produced. So many of the talk is inspired by the school of Brown. Okay. It's good to cite him early. And the school of Geoghegan. I can't cite Brown without citing him. Alright, so that's one example. Second example where you have it here, where you have AA is EB. So here I'm going to complete my graph. Okay. This will also give you a group, and that will give you a group due to Cleary actually in 2000, which is sometimes called the irrational slope Thompson group. And there have been some very recent articles who look at that are due to Peck, Burillo, Nusinkis, and Reeves. Okay, so that's 2020-21, I believe. So it's kind of like the Thompson's group, but you work with a golden ratio here. It's very similar to actually the Frobenius algebra that we were looking this morning, but just the classical golden ratio. Right, so that's one example, and now I'm going to put another example that we're going to see it later, so I will give it a name. So I call it the rebel example, the rebel category. Okay? And you will see why after. So this one has two colors, but it has two relations. Okay? So maybe I write it like that. Is that understandable what I'm writing? Okay. Maybe I can add the stuff here. That's this relation, and then it commutes on the line. Okay. So if you look at a line going up left, it doesn't matter the order of A and B. And if you have A squared, that's the same as B squared. This will give you a group. And here it's actually not so trivial to understand exactly what it is, but I'm going to tell you exactly what it is. It's a generalized Riesz product with Z2. So by Z2 I mean Z mod 2. Here I'm going to put the dynamic rational of the circle, and I'm acting on it by the Thompson's group. Okay. Classical action. Okay. So it's a generalized Riesz product. Permutational of Riesz product, I mean, and a restricted one. Okay. I put it here because it's such a simple extension of Thompson. It's actually very hard to understand its topological properties. Okay. And it actually, so it's just a good example to show you that some techniques fail. But nevertheless, one can say what they are. Okay, so I give me already 3 examples of categories and some groups. So explain what was a forest category is. Now I'd like to construct groupoid and groups. So I'm only interested in 2 groups. And if I want to construct groups, I need to invert elements of groupoid. And so I want a calculus of fraction. I want a very nice way to invert elements. So if you want to have a calculus of fraction for a category or a monoid, let's say, there's 2 conditions you can ask. You can actually have weaker than this one, but for everything that I need, we need this formula. So first condition I want is to be left cancellative. Okay. So if you have equalities of 2 forests, then you have like a common subtree, let's say, and you can remove it and still have equality. Okay? So you can simplify by the left. So it's true if I don't put any relation, but you guess that if I add a lot of relation, it may not be true, right? Okay. If you want something not left conservative, you can simply imagine you have the relation. I'm just going to put A for 2 of them, and then I will put something different on top. Okay. So for example, I have this, and here I have that. So this is not left conservative if you have this single relation, because it starts by the same stuff here. Okay. So that will fail to be left conservative. So if you don't like that, just think in terms of monoids. Okay, so take the 3 monoid into generator and quotient by words that start by the same, that have common prefix. So that's one thing I want to do, the second thing that I want is existence of right common multiple. Okay? It means that if I take, let's do it with trees, I take 2 trees, I can find a large tree such that these 2 trees are rooted subtree of it. So actually it's sufficient to do it for 3. For any ST, let's say, trees of F, there exist FG that are forest, such that S composed with F is equal to T composed with G. Okay? So up to growing them, at some point they will be the same. So you have the choice, you take the one you want. And here is the key part. If I take my free version here and have at least 2 generators, it never satisfies that. Okay. So you cannot. So it's tempting to take these 3 forest categories, but they will never give you group. Yeah. So you need to mod out a little bit. Okay. Right. And if you mod out too much, you may no longer be left conservative. So there are 2 conditions that are kind of opposite to each other. Right? Okay. So if you satisfy these 2 conditions, you say that you have let's say a left calculus of fraction. So this is quite old. This was done in the 60s, very well done by Gabriel and Zisman, for example. And in fact, for monoid, that was done in the 30s. Okay, for non-abelian monoid, this is really how we did it, and it was not published, but it appears in the work of Malchev shortly after. Okay, and decide correctly. So often this is called OR property, or OR categories, whatever. Okay, so maybe I can say the fact, and perhaps I can say OR, is that if F satisfies, so I'm going to call it maybe AB. Oh, that's not good for my colors, so let's say I and 2I. Well then, we can formally invert the forest. Okay? And everything goes well. And so that gives me what I call the forest groupoid. Maybe I stop saying groupoid, forest all the time. I get a groupoid that I may write like that. Frac is for fraction. Okay, I will explain it why. And I got a group, my favorite group, and I will explain what it is in a second. That I write F, and here I put a 1. Right, so elements of frac G, frac F are of the form, they look like one forest composed with a formal inverse, okay? Fg forest. And here what you have is that the number of leaves, maybe I write it like that, is equal to the number of leaves of G, okay? The number of leaves. So element would look like if you can write it as you want, but you could write it, for example, so that's an element of my fraction, and perhaps I can write it like that. So people who like algebras, they start to recognize some classical thing. Okay. All right, so that's the element of my fraction groupoid, and you can multiply them. And what is nice is that any words in positive and negative powers, they can always be written with 2 letters like that. Okay, that's what is great. Right? So if I have if I compose with the H, up to changing these 2 guys, I can remove the H. That's what I mean. Okay. Now frac F1, they are just pairs of trees.
How do you see that?
The one is for the. Oh, how do you see that? Oh, that comes from this condition. Like the Hauss property, the existence of right common multiple, will make that if I put a H at some point up to drawing them, they are the same thing. Okay, so. Yeah. And so if I look at just pair of trees, that give me a group, and I can multiply it. It's that's the automorphism group of my groupoid F at the object 1, for those who prefer the category term. Here we only deal with small categories, so everything is set with operations that are sometimes only partially defined, but that's how it's a good way to think about it. It's just an algebraic structure. Okay. And so for those of you who've seen the Thompson's group, perhaps you remember that any element of the Thompson group can be described by a pair of binary trees with the same number of leaves. Okay. And now you can amuse yourself to put several colors and see what happens. And so actually what did Burino, Lucic, and Reeves, they actually give a very similar description for this specific group. Okay. And they studied, and they realized that they had quite a lot of common properties with Thompson group F, continuing the work of clearing. Right. But what is amazing is that if you take this general framework, you can look at many other examples. So for example, if I want to generalize the example of clearing, what can I do? I could define, let's call it Fn. So it's going to be 2 colors again, but now I'm going to put trees with, let's say, n caret. Okay. Or n interior node. Okay. So this gives me a category with a calculus of fraction, and that gives me a group. For any n. And moreover, what is nice is that you can even show that they are pairwise and isomorphic, this group. So how do you do that? Well, you can look at the abelianization, and you can see that. So if I look at maybe I call it GM. You can look. So isomorphic is that. Okay. Directly or different. Okay. So that was the calculus of fraction. So why am I looking at that? So I'm going to try to be, it's very important actually, but I try to not do the whole talk about that. Because the name of it. Okay. Well, I guess I'm going to erase that. So the starting point, why I look at that, comes from the reconstruction program of CFT of Vaughan Jones. Yeah. So I'm going to explain that. And also of this novel Jones technology that's been introduced quite recently that allow you to construct many action of groups when you have the extra structure of underlying category. So the idea was to really find nice categories with calculus of fraction for which you could use efficiently this new technology of that Vaughan introduced very few years ago actually. A bit less than 10 years ago. Okay. All right, so let's look at the motivation. So there are quite several motivations. So first one, that's this program linking Jones subfactor theory and conformal field theory. So that's a program that exists in the beginning of subfactors. There's been many people who contribute to it. I think the first connection perhaps came from Longo in the 80s with the index, right? In the Toplicher-Grober's context and Jones index. And then there's been the Longo reconstruction in one direction, and the other direction is very tricky. So for example, I can cite David Evans, who's here in the room, who work quite hard on exotic subfactors, trying to get some physical theory out of them. For example, the Agro, the extended Agro. I mean, I can cite quite a lot of people, but it will be quite long. Anyway, so one last attempt that Vaughan did to try to construct CFT from subfactors was to, the scheme can be explained quite quickly. You would take a subfactor, you would look at its planar algebra. Okay. And from there, you will choose, you make a choice. You choose one element inside your planar algebra. That is an isometry. It means that if I compose with a star, it gives you just an element. And from there, you have some kind of lattice approximation, a quantum chain of a field theory, or what you would like to be a conformal field theory. And the refinement maps were given by things like that. So you will have a certain number of points on a line or on the circle. If you want more points, well, maybe perhaps sometime you're going to add your map here, okay? And it'll give you more points. Okay. Okay. And so you get at the end of the day some kind of, you mimic the conformal field theory, but now the symmetry group, instead of being the diffeomorphism of the circle, become Thompson's group F, Thompson group T. Okay, and so here the whole idea is to get a more sophisticated group that is acting. And to have like a lattice approximation that takes more part of your planar algebra. So the idea here is very simple. If you want, I'm just going to write like that, is to take or choose several such R. Okay? And the choice will be dictated by your subfactor, okay, your planar algebra, just like here. Right? Vaughan was always saying that it would be very interesting to understand what's going on if R will be the generator of the hyperloop subfactor, okay, that Emily gave in this thesis. And so here, it's a bit the idea is to take several of them, several of the generator, and see what you get. Okay. How much representation theoretical information do you keep by doing this approximation of your CFT? That's completely open. So that was the first motivation for this work. Yeah. The second, that has been actually redriving my research this last year, is to use Jones technology. So let me explain very quickly what it is that for F, as I was saying, the Thompson group is built from the category of binary forest. Okay. Now this binary forest is generated by a single caret, right? Because there's only one column. And then realize that if you take this caret and you go to any category, you just take a morphism, let's say from an object to its second tensor, okay? Just this data give you an action of Thompson group F. Okay. So it's a wonderful machine for constructing action of very complicated group like the Thompson group F, but like you almost pretend that your group is cyclic now, because you only need one map. But the cost is that your map don't go from E to E, but you need to double the tensor. And in fact, this technology right here, if I present it like that, with tensor product, you can extend your action to the largest Thompson group V. For those who know. Right. So here the idea was to find groups for which this ID will be useful, where you will be able to construct very easily actions. Okay. There is a third, well, it's linked to that, so I'm just going to say it orally because if not, it's going to be too long. From this ID, there was this Pythagorean sister algebra that Vaughan came out with, and he invited me a bit later on the project, so it's really him who found that. And that was basically to look at morphism like that. So if you take that and you associate just an isometry with H being just a Hilbert space, okay? Well, this gives you a unitary rep of F, okay, of Thompson group F. That's quite an amazing thing to construct unitary representation. And from there, you want to look at a certain sister algebra, which is just generated by two elements, and satisfies this relation. Well, now I'm writing it up here. And what you realize is that so that was the Pythagorean key that one came out with, is that you have a map going from rep P to the representation of the Thompson group F, and moreover, that's very interesting, there is a way also from the representation of this one to get the representation of the Kuntz algebra. So Kuntz lives below, but by some kind of broad construction, you can get representation of Kuntz using, if you wish, only finite dimensional data. And this, remember, I was talking with Adam Sims about that, and he was in shock. He said, what, you can construct representation of Kuntz using just finite dimensional matrices? Yeah, you can. There is an inductive limit process, but everything is very complete. So that's very powerful. And so that's also something, each of the group I'm going to show, each of these categories gives you a similar sister algebra. And this sister algebra has very exceptional properties. It's non-nuclear, and it satisfies the property of lifting property, the lifting property that was proved by Christine Courtney a few years ago. I think it's from 21. And so you see, you have a very rare actually sister algebra, so why not trying to construct more of them and use them to build a bunch of representation of more complicated sister algebras. Okay. So third motivation is actually one of the talks, so I see that I already run out of time, which is to build interesting groups. Okay? So forget about the reconstruction program for a moment and just see what kind of group you can do. And using all these tools, what can you say about these groups? So that's what I would like to emphasize today until the end of the talk. So I'll be brief, I'm sorry. But yeah, that's kind of the last topic. All right. Okay, so let me just put the key feature of this formalism. I'm just going to write the application you get from that.
You have 15 minutes.
15 minutes, yeah?
Yeah.
Okay. Okay. So the first thing that I think is the most important point, actually, it's given a certain F, a certain Forest category, it is easy or possible to decide if it has a calculus of fraction or not. And to me, this is the most important point of this formalism. That actually you can easily decide about that. Okay? So you know in planar algebra you say, okay, I have this generator that satisfies this spin relation, but then it's the hardest thing is always to show consistency. That you actually have something, it does not collapse to zero. Here you have this formalism, it's much easier to say it. And the tool that you use is the work of de Ormois, basically from the 19th to 2010. Okay. The work that de Ormois did on monoid, extremely useful here. So thanks to de Ormois and thanks to this particular formalism, it is very easy to decide if you are left conservative or not. Okay. It is difficult still to know if you have command right multiple, but at least you did half of the work. Okay. In general, you give me a monoid or a category, there is no way to know these two properties. You need to check example by example, but here we have the lux to almost forget the first one. Okay, so that's really nice. That's really a consequence of the choice of the formalism. So for me, it's like perhaps the most important thing. So second, what do you get? So the extra structure of F for studying this group of fractions, so I'm just going to call it G, that group, gives. So what does that give me to know that my group is built from a category that I know? Okay. Well, first, as I was saying, you can build many actions. Okay. So that's just using Joe's technology. Okay? They are built from that. They are built for that. Okay, that was second thing that is really nice. Well, you have a sister algebra associated to it, but I want to study my group. What you have is you have a very nice classifying space. Okay? So you can just take the nerve of your category F, and from there you have a very small classifying space. So every group has a classifying space, but you know, there's a general construction, you get it. But having this category under it makes that it has a very nice space, this category, this classifying space, okay? And so, using it, you get some very small and explicit presentation of G, a bit like Thompson if you want. You can just derive, there is an algorithm, you give me like a Forest-skein presentation, I give you a group presentation. Explicitly. And since I have a, okay, here's one thing. They are also T, so if you don't know the Thompson group, it's going to be a bit hard to explain. TV and BV version of G. So what do I mean by that? Thompson's group acts on the interval. There is a version that acts by Omeo on the circle. You make it even bigger, it acts on the cantor by Omeo. And there is a braided version of it that is due independently by Arnaud and Brothier in 2006. Each of my first category give me a group when they are the calculus of function, and I can create, in fact, 3 other groups, the TV and BV version. So I can braid them, all of them. And that comes from the fact that I have a category. Okay, they are built from categories, so I can do that. And last thing, which was supposed to be my main result, maybe I will have time to give it later, is that you can often decide about finiteness property. Okay? All right. When I say finiteness, I mean topological. Because of the technique I will use, well, you know that they are equivalent for finitely presented group to the homological one. Okay. But here all the techniques they are topological. Okay, so perhaps I'm just going to write one theorem that is combine a bit all these ideas or groups, and that would be it. So I should say there is a lot of group, family of group that has been constructed that are similar to Thompson, but about basically all of them, they are built from the perspective of piecewise linear action. Okay. So it has very good advantage because, for example, it would be very good to test simplicity properties. The categorical framework is different, but you saw the motivation are not exactly the same, but they are not purely from group theory. But the advantage would be that they will work better for topological properties, I mean, at least they will work very well. And you still get some simplicity also, so that's kind of nice. Why are the Thompson groups so famous? Well, first thing, because nobody knows how to show that F is amenable or not. Second, because they provide the first example of infinite groups that are simple and have good finiteness property. Okay, so T and D, they were the first example actually to be finitely presented. And after we realized that all of them, they have type F infinity, which is the strongest way to say they are finitely presented. Okay, so that's already quite old, that's the 80s from Brown and Gagan. Okay, so let me give you just one theorem. All right. Okay. So pick 2 trees, 2 unleveled trees, like I don't know, whatever. This and maybe this one. Okay. Maybe I call them T and S. from there, you can look at the forest category, let's say with two colors, where T will be, so if you want, I color in by AT, so all these vertices, I put some A1, and I'm going to color also the second guy, but by putting some B's. So I took this guy, and basically my relation is this, okay? Okay? Easy example. Great, I have a calculus of fractions. So first thing, okay, there is a calculus of fractions. So I'm happy. So left considerability is given by the order. Thank you. Or property, existence of right common multiple, is because they are monochromatic. This guy are only A, this guy are only B. If I mix them, you can get up early, before the first metro, to try to prove they have it for large families. It's yeah. So I found that after checking many families, like some one parameter family, and then I realized that if you have only the same color, a miracle, like an easy proof come out. But if you don't, there are really interesting examples that show you that there is not much intuition. Okay, it's hard to build intuition when you have common right multiple. This I was super happy to get that. Okay. And the second thing, so they give you, let's say, a group. Maybe I call it like that, GTS. And now GTS, well, I have an explicit presentation I can give you, but also it's finitely presented, but it's of type F infinity. Okay? So what does that even mean? It means that for any n, I can find a classifying space with finitely many cells of dimensions smaller than n. Okay. Right. So the strongest condition going after being finitely presented. Okay, so there's F2, F3, F4, F5. And if you are Fn for any n, you call F infinity. Okay. So they are all like that. So it's quite exceptional. And moreover, you can look at the T, V, and BV versions. Okay? These are all of type F infinity as well. Okay. Yeah. So in general, in the literature, if you want to prove that the Thompson's group is of type Fk or F infinity, and after you want to prove the other version, you need to do the proof separately. Okay. So this is the case for the F version that is here, V and BV. But there is a trick to go from here to here. It's kind of fun. Yeah, no, okay, I don't have time to do it. But let's say that this trick never works in general. It only works for the initial Thompson's group. There is a strategy in the original paper of Brown and Gegan that they get. But I don't know any other family when you can do that. But here you can. Very nice. Okay. Yeah. Well, I think I'm already out of time, so I just stop.
You have a meet but well, if you want to.
Well, let's say that, so this theorem, here I have two colors. I could take any number of colors that I want, actually. And as long as they are finitely many, they will be of type F infinity. But I can take infinitely many, I will still have groups. So that's pretty nice, yeah. Yeah. And I was talking about the Cleary group before, you know, when you have like those two vine of unicolor vine, you know, I was saying like you have groups of lengths with n carets in it. Well, this is covered by this theorem that they exist. Okay, so they give you a new one parameter family, but they are much more than that, which is really nice. Yeah. So you can amuse yourself to see which one are isomorphic. So 1, 2 to show they are different are the abelianized group when we model it by the derived group. But I built this group with categories, and guess what? What can I do? They seem to be very nice for computing homology, higher homological group. So with that, I haven't done it yet, but I'm doing a lot of computation, but I can't believe I can do it, and that would be a better key to show that they are different. Right. Okay, but I already stop here. Thank you very much.